Hello, my name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you have chosen to join us today. Let's go inside. The lecture's about to begin.
Today we have a distinguished lecture by a distinguished lecturer. Again, I'm really pleased and proud to have our guest today. I know this is going to be a really worthwhile and exciting presentation. And as is our usual procedure, I'm going to describe to you some facts about Professor Juris Hartmanis that are not known to many or any of you. We do not give the usual introduction, but rather a description as to what turned him on to this field in which we are all so deeply engaged. To quote Juris Hartmanis, Latvia is a lovely little country lying in the shadow of two 800-pound gorillas. And I'll let you figure out who they are. His father was a high-ranking military officer, and as a result, he was destined to attend one of the top French military schools. But as that was about to happen, another event took place, an event known as World War II, and interfered with that progress. As the Russians and the Germans traded Latvia back and forth, finally, when the Germans had control, they decided to send Juris to Germany. And that was in October 1944. And they sent him by ship. Shipped him out by ship. At the end of the war, he found himself stranded in a Europe which was totally divest of everything. Physical plant, morality, ideology. In the midst of a terribly unstable situation, as I suspect all of you would do, he looked around for something which remained stable. And one of the things which was stable, it turns out that the Germans, although they burned books in one part of Germany, their science libraries they kept. And Juris took advantage of that, and he found a book, fortunately, by Edinger on astronomy and physics, and he got terribly interested in the field. It was amazing to him that amidst this chaos, something remained pure, and in fact, science and mathematics does remain pure in spite of the world wars. And at the same time, he attended some high school training there in Germany at a Latvian school, and was the beneficiary of education presented by some of the best university professors and academicians who had been thrown out of university and ended up continuing their trade as high school teachers. So the level of calculus and physics and chemistry that he experienced as a high school student matched that of any fine university around the world. So he was well prepared. He then spent 2.5 years at the University of Marburg studying physics. Then he came to the United States in 1950 and went to the University of Kansas City through a sponsor, and that's why he ended up in Kansas City, on fellowship. The University of Kansas said he had too many credit hours to become a bachelor's student, so they gave him a bachelor's degree. They had no graduate school in physics, which is what he wanted, but they had an advanced program in mathematics, so what? He studied mathematics. Okay. He was then admitted to Caltech as a TA, but the reason he chose Caltech over other places is because they paid his way out here. So these are the vagaries of chance that manufacture a career. On the other hand, they told him they had no applied math program, but they had a pure math program, pure math. He studied lattice theory, etc., went on to Cornell as an instructor, and it was the tradition in mathematics in those days, as often is today, to become basically an instructor before you get onto the permanent faculty. He was seduced by GE research labs in Schenectady on a summer job, and there first experienced problems in computer science. And at that point, he turned to the field of computer science. He spent some time at Ohio State with Marshall Hall, went back to Cornell. The rest is history, and some of the history you're going to hear today. But in fact, I did ask him, as always, what message would he leave with a group such as this? And his message is the following. He's immensely impressed by the technology achievements in computing, but he's most impressed by the science side of information and computation. And we're going to hear that today, the title of this presentation, From Goedel to Van Neumann, and Van Neumann to Interactive Proofs.
Yes. Thank you. Wow, it's a strange feeling not being able to see the audience clearly. Anyway, I'm delighted to be here, and what I would like to do is describe to you some of the intellectual development, historical development, intellectual ideas which led to concept of computability and complexity theory, and finally to some very, very interesting recent results about interactive proofs, which, as you will see, give some very nice insights into the basic nature of theorem proving. And I will start with some oversimplified history, and apologies that what I will say will probably be known to quite a few of you already, and I hope you view this as retelling a story, not for the individual facts, but primarily for the flow of ideas and their developments. When one wants to look very, very simply at where the origins of computability come from, the concept of computability, one can go back to Cantor's sets theory, which was created just on the turn of the last century, and which provided new foundations for mathematics and some very interesting developments there. When one looks at that, Cantor already talked about the different sizes of infinity, that there are more real numbers than rational numbers, and so on. And if one looks at that, already the seeds of unsolvable problems, of Gödel-type incompleteness results are there, because we know that if we would think about programs, there would be only an innumerable number of programs, infinite but innumerable. If we would look at functions, Cantor easily showed that there are more functions than there are programs, though he didn't put in those terms. So the seeds of that were already there. Unfortunately, with set theory came all kinds of nice contradictions, and here is one of them. Look at that set defined as follows, then rewrite what this means. That just means that y is in x if and only if y is not in y. Since we talk about sets, plug in x for y, and you have the bottom line, which is quite troubling to any mathematician. Now, you heard this usually talked to in English. This is a kind of greasy proof or greasy presentation due to David Grease. Now, Hilbert was one of the leading mathematicians, David Hilbert, at that time, and he was deeply concerned about the struggle in trying to understand what was wrong with set theory. And he said, basically, the trouble is that you people don't know what you're talking about. You are mixing up your intuitive concepts with mathematical concepts, and you're getting in trouble. He said, I will tell you how to do mathematics. I will axiomatize it, write down a set of axioms, rules of inference for bigger and bigger parts of mathematics, and then I and my friends will prove that these axiomatizations are complete and consistent. You're going to prove only truth theorems, and you're going to prove all possible truth theorems in these systems. And life will be very easy. That was a heroic view of what mathematics could do. And just to show you who was the person, here is David Hilbert, and please, I hope you can read the bottom line. Can you read it?
Yes.
It says, David Hilbert, 1912, one of a group of portraits of professors which were sold as postcards in Göttingen. Those were the days to be a professor. I am sorry to say that even in Ithaca, they don't sell postcards of professors. Well, Hilbert's idea really was tremendously grandiose. And if you see how he looked later, in 37, you may appreciate that it didn't work. But I know this was said a little bit facetiously. Hilbert really was a great man, a very, very interesting person. And there's a lovely book about Hilbert written by Constance Reed, simply called Hilbert. If you have not read it, please do. It's one of the delightful biographies of a great mathematician. She has also, Constance Reed, has written a book called Life Story of Courant, which is also very interesting to read. And she's currently writing a book on Eric Temple Bell, and I will let you figure out who Eric Temple Bell is. Well, what's interesting, that Hilbert should have known better, that it will not be possible to axiomatize mathematics completely and consistently. But it's interesting that it wasn't only Hilbert who believed that that could be done. This elegantly attired man also deeply believed in the same, and that's von Neumann, who did many, many other interesting things, who was super bright and gifted, and who worked with Hilbert in trying to axiomatize mathematics. Now, so they were off trying to do what was not possible, and a little bit facetiously I can say, please look at this picture. I hope you can make out, no, you can't very well what's going on. That's the Grand Canyon, and this picture doesn't show it very clearly. And all these people are going to descend on their mules in the Grand Canyon. And you know how casually they are dressed and how they all look down. And there's somebody up there. That's von Neumann. His donkey pointing in the wrong direction. And he's dressed in his business suit. Necktie and everything. Now, his father was a banker, so maybe you can forgive it to him. And he loved powerful and rich people, and really was very, very successful in his life as a scientist and influential in science policy after World War, during and after World War II. And anyway, as you know, he was trying to go the wrong direction. Well, as you know, along came Kurt Gödel, and in 1931 showed that number theory cannot completely and consistently axiomatize. If you have a consistent axiomatization, there will be results which you cannot prove in that system and which are true statements in number theory. Well, what's interesting that when Goedel did this, he did not have a clear concept of what is and is not computable. He did not have a precise definition of computability. And I think his genius is visible that he could shoehorn back in all this argument, which is basically an argument about computability, into numbers theory and prove that the axiomatization cannot be complete and consistent. Well, since I've shown you pictures of other people, here is Kurt. An amazing character again, a very strange and interesting person. And I hear often laments that computer science doesn't have, that physics and mathematics have their heroes and so on, and that computer science doesn't have very colorful people. That's nonsense. We have lots of them. Now, these in some sense are borrowed from mathematics, but they are really influential in shaping the developments of computer science. Here are just some facts about Goedel. And as you can see, Goedel lived quite a long life. What's interesting, that when Goedel passed away, the death certificate said that one of the causes was malnutrition. He followed religiously a very strict diet, and basically after the death of his wife in a few years starved himself to death. Well, the concept of computability, as we all know, came from, the concept of computability was worked on by quite a few people. The intuitively most satisfying definition was given by Alan Turing, Alonzo Church, Post, and many others struggled with that concept. But Turing gave this very, very nice definition. And as you know, what Turing showed was that the set of machines, Turing machines, can be enumerated, can be listed 1, 2, 3, and so on. And that list can actually be produced by another machine, one. And second, that there was a universal machine. There was one machine, as long, M sub u, as long as you told you what machine you want to imitate and give an input, it would do exactly what that machine would do on that input. Please note that this here is exactly the concept of an internally stored program computer. It's there in a beautifully crisp mathematical form with a nice proof in Turing's paper. And he showed that there were many undecidable problems. Okay? And what he had done really now is simply saying, look, whatever computing devices you're going to have, there is a innumerable number. I can list them all. Okay? And that alone told you that there is trouble, that you cannot compute everything you want to compute. Okay? And the theory of computability was developed from this point on. Well, I think I should show you how Turing looked, and that's Alan Turing. And what did Turing do? Turing was a superbly original human being. He tried to do almost everything from scratch, and I think one of the most successful things he did was really inventing the Turing machine. But it's interesting that recently, several of his ideas have been experimentally verified. He thought about quantum mechanics and realized that there seemed to be an inconsistency. In quantum mechanics, the observer is an essential part of the physical description, and he, looking at quantum theoretic foundations, realized that he could freeze the processes in quantum mechanics by continuously observing them, because the observer stops the process. And this was ignored by the physicists. That was just fun. I mean, Turing was off looking at funny contradictions. Well, recently people carried out an experiment. They took a molecule with slowly changing states, poured in lots of energy, and slowly the molecules were raised to a higher level of excitation. In essence, as I said, they started boiling. And they poured in some more energy by laser beam, observing these molecules. And lo and behold, as they pinged them a few times, putting more energy in, a lot fewer boiled. A lot fewer were going up to the higher level. And if they repeated more often, fewer and fewer got to a higher level. And so a tremendously nice verification that really observing that phenomenon, you could slow it down. You can kind of almost freeze it. And you know, the article on this had a lovely title. It says, what is it? A watched pot never boils. And so, but it's very interesting. He did lots of other things. He was interested how tigers develop spots. You know, how would you explain that? And he concocted a very interesting imagined a very interesting chemical distribution, with different densities and so on, which would create such spots. And lo and behold, during the last few years, chemists really cooked up such concoctions, and indeed the spots appeared. And so our article said, Turing's spots are real. And it's interesting that these were really very original persons looking at different areas and almost every time spotting something interesting, totally unappreciated by the people who worked on these areas. Well, very quickly, Turing did many, many things, but he went to the Turing machine, and I want to point to this part. Turing spent 1937 to 1939 in Princeton, met von Neumann. Von Neumann attended his lectures. Von Neumann clearly understood exactly what Turing had done. Turing had invented the internally stored program machine. Von Neumann understood it. Von Neumann even understood it so well that he offered Turing to become his research assistant. Turing turned it down to go back to England. War was threatening. And as soon as he got to England, when war started, he was deeply involved in code cracking. He was involved in building the Colossus or the Enigma machine to decode German codes, primarily naval codes, but many others. And, you know, World War II history has to be rewritten, and it hasn't been rewritten, in terms of the information which was available to the Allies. And the English guarded those secrets so well. When the early history was written, none of that was known. You know, Stalin was continuously informed about German military plans, German military situations, and so on. And never, ever was uttered by Stalin and anybody in Russia that they were being fed by the Allies total information about the German intent, battle plans, and so on. So anyway, I want you to remember where Turing was and what he was doing. And here is just a very quick picture of the Colossus in operation in 44, 45. It was probably one of the very first functioning electronic computers, so it was not universal, but it could easily have been made universal. It was used primarily, well, was used only for code cracking. Well, why not? There's Turing winning, getting second place in a race. And there's Turing's machine. Now, you know, in those days, machines were machines. and this one is a small one, you know, compared to ENIAC and EDVAC and those. I mean, when basements filled up and lights dimmed in the buildings when they turned them on, and so on. Well, please note that Turing is a long-distance runner. Turing was quite good at it. Turing was not so good a chess player. But he loved to play chess. And so he invited people to his house, which has a nice garden. They had tea outside, and he took a chessboard out and said, let's play chess. And they said, fine. And he said, but I don't have a chessboard. Ah, said Turing, let's do it as follows. You make a move, you walk around, come back. By that time I have to make a move. Then I go walk around, come back. Apparently, he very rarely lost any games that way, but his guests were startled when after making his move, he took off like a rabbit. Well, this is in some sense, trying to do a little bit of historic justice. Emil Post was an American mathematician who taught in high schools for quite a while, and then at City College in New York. And Emil Post, in essence, had Gödel's incompleteness result. But he lacked the concept of computability. And therefore, he did not think that he should publish that result. He wanted to really do what Gödel and what von Neumann, Gödel and Turing did. He wanted to do all by himself, you know, and Gödel published his result. Post was kind of left out in the cold, and then Post tried to really arrive at the concept of computability, arrived at a very, very similar formulation as Turing's, just about at the same time. Turing's is done in terms of a machine. Post's was done more in terms of programs. And so Post then went on to really demystify the Gödel result, put it in terms of computability, in terms of recursive function theory concepts, and I think was very, very instrumental in development of recursive function theory. While we are mentioning some pictures, by the way, I was told that a picture is worth 1,000 words. Then I tried to figure out how many words are there in a lecture. And somebody assured me around 1,000. So please realize how many equivalents of 1,000-word lectures you're getting for pictures. There's our friend von Neumann. And there is the ENIAC. And please note what they say, that Mr. Goldstein is setting function switches. I'm showing you function switches. You know what that means? No internally stored programs. I mean, they really set switches to give the function values, and they plug boards to drive the machine. Well, von Neumann consulted for them and said, you have made a mistake, it should have been an internally stored program machine. He and Goldstein and others and Burks wrote a very, very important document, how machines should be designed, what the logical design should be of computers. That influenced everybody in the world, just about everybody in the world. And von Neumann then marched off to build his own computer, Institute for Advanced Study. The institute hated it. They did enough experimentalists, and they didn't see why the machine should be built, but von Neumann was so successful and energetic that they couldn't hold him back. By the way, is there anybody who knows what these gadgets are down here? These coffee pots. Yeah. Williams tubes. Those were holding vacuum, cathode ray tubes holding small amounts of information each. What's amazing, that when they started building the machine, they didn't know what their memory would be. Before that, the best they had were tubes filled with mercury, which they pinged electronically at the end, and the waves represented zeros and ones. And when they arrived at the other end, they restarted them, or they could change them. And so those mercury tubes, the wave represented zeros and ones. Can you think of programming such a machine? Anyway, what I'm really showing is that the ENIAC was definitely, absolutely not internally stored program machine, and von Neumann certainly built one later, which was. So did Eckert and Maunchley of the ENIAC fame, who went on to build the EDVAC and so on. And what's very interesting, that people have struggled to understand whose idea it was. There were lawsuits of all kinds. IBM was sued by Honeywell to break Eckert and Maunchley patents. They did. The lawsuits declared that Atanasov had the first functional electronic computer, or parts of computer. And Neumann was given opportunity to clarify where he got, how he invented the internally stored program machine. He never did. And look, I'm deeply convinced that that comes straight on Turing's ideas. But it was too big a thing for von Neumann, who really didn't need the glory to admit that that wasn't quite his own. Well, anyway, Eckert Maunchley also believed that they had done that. And there's just one more picture of Goldstein. That's a different Goldstein than the one who was setting the switches, and clearly Oppenheimer, whom you know, had a very interesting and semi-tragic life. Finally, one more picture, another 1,000 words. Note that happy-looking guy, pudgy, happy-looking guy, again in his business suit, telling probably, that's probably true, but somewhere in this period, when they dedicated a powerful IBM machine, powerful by those days, when von Neumann estimated that more than 10 such machines would never be needed in this world. He really did. Well, anyway, so computability theory was now defined. Gödel thought that Turing's way of defining it really clarified it. He said psychologically that's the most satisfying definition. And he actually said he thought it was a minor miracle that a concept of the sort like what's effectively computable could be so crisply and so nicely defined. And Goedel published really very little when you realize how famous and how influential he was. But he was sitting at the Institute of Advanced Studies in Princeton. His colleagues were von Neumann and Einstein. And these people had been there for many, many years. They were all American citizens, United States citizens. And then in 1956, Goedel writes a letter. And as you see, it starts out, Lieber Herr von Neumann. It's amazing that after all these years, these people still, when they met, always talked German to each other, that they addressed each other formally, Lieber Herr von Neumann. I mean, they saw each other daily at tea. Sorry, they drank tea at the Superman study. And he says, I'm terribly sorry to hear that you are sick. By the way, I hope I'm not offending you by trying to translate a bit. And then he says, now that you are feeling somewhat better, I would like to pose a mathematical problem. and he proceeds simply to say, you know, let the formula be basically in predicate calculus. Predicate. Im engeren Funktionenkalkyl. And he says, let the length of a proof be n, and he says, length, I just mean number of symbols in the proof, and so on. And then says, let this be the number of steps I need on a Turing machine to decide that the theorem, or formula F, has a proof of length n. And then he says, and now take the optimal algorithm, and let phi of n be the max over all these formulas, and then let phi of n be an optimal algorithm for that. And he says, how fast does it have to, can it work? So in essence, Goedel is saying, how long does it take me to decide, when you give me a theorem, that there is a proof of length n for that theorem? That, ladies and gentlemen, is a question about an NP-complete problem. That is the question, really, how hard is it to solve problems which I can guess the solution and verify quickly that you give me when you give me the right solution. That's a key problem with which you have struggled for a long time. And then Goedel says, well, he can't prove anything better than linear time. It would be still nice if one could prove, say, that that's the best you could do would be n squared. What an illusion. If we could do that, God, computing would be nice. And there would be something very, very deep about computing which we do not understand. If that would be the case, because then P would be equal NP, and I trust I don't have to explain P and NP to you. If I do, you should send your students to Cornell. Please note that I wrote down here the department archives at the Library of Congress had 40 boxes of von Neumann material. I did not have the expertise nor the time to try to search through them, seeing whether von Neumann ever answered. Because wouldn't it be surprising if there would be a nice letter from von Neumann saying, Lieber Herr Goedel, your problem was very interesting, and here's the solution. It can be done in MQ time. What would be really upsetting if there would be such a thing, but I don't have enough space to write the proof. Right? I mean, anyway, letter, by the way, is just, one should dwell on it because it's so delightful. He then goes on and says, look, one shouldn't be so shocked because maybe there's something better than the brutal prime of all possible things. Because he says there are things which go from n steps when you need to log n steps when you're clever. You come to real problems. So he was even optimistic that could be done fast. He then also goes on and says, it's interesting to discover how fast we can check whether a number is or is not a prime. You know, which we have struggled extensively with primality testing and so on. And then, very delightfully, he says, oh, and by the way, have you heard that a young man by the name of Friedman solved a post problem in the positive? And then he says very charmingly, unfortunately, Friedberg will not study mathematics. Under the influence of his father, he will study medicine. And anyway, then the letter ends. I find that letter, which I came across almost by accident when somebody came in and said, why is Turing's name mentioned in this letter? The person was interested in Turing. And I looked at it, and after a few minutes I said, my God, this guy is really asking, how long does it take to compute an NP-complete problem? Well, clearly at that time, for Neumann could talk, kind of hoping that maybe it's n squared or something like that. I don't think he fully appreciated that it's very likely to be exponentially hard, basically testing whether it is or is not a proof for a theorem, sorry, of length n, basically will require exhausting all possible strings of length n, or something damn close to that, which we believe is the case. But clearly we have no proof of that. And so let me just say that in modern terms, Goedel's question was, how hard is to solve NP problems? Now, the richness and the importance of the problem which Goedel is asking for Neumann was not really appreciated by, I think, even by Goedel. The understanding of that really came only after Cook's work on NP completeness, when NP class was defined as a class, you know, of all the problems you can solve, is guessing and quickly verifying. And as you know, Cook showed that every NP problem can easily be reduced to Boolean formulas, which are satisfiable. Maybe I'm writing Boolean formulas conjunct in normal form, and can reduce every one of these guess and verify problems to a formula. And if the formula is satisfied, namely if I can assign zeros and ones to these variables, and if it evaluates to 1 or true, then the problem is solvable. And if not, the problem is not solvable. Or the problem has a solution or it doesn't. Now, that was a beautiful and deep insight by Cook. And as you know, there were hundreds and hundreds of problems discovered for NP complete. In just about everywhere where you looked, the problem popped up of the sort. The solution space is very large of feasible possible solutions. It's exponentially large in the problem. And we have no way, we know no way of how to find a solution. But if you give a solution or assert something a solution, it's very quick to verify whether it is or is not a solution. And clearly, people have worked very, very hard on trying to prove or disprove that problem. And let me just give you one more fact which will appear a little bit later, and that is that when we look at not at non-deterministic computations, but at polynomial space computations. So I give you a polynomial amount of space in the length of the problem, and you can write and erase and reuse the tape as much as you want to, okay? And so you can search for all kinds of possible solutions and so on. So that's polynomial tape or polynomial space. I mean, or you just think of it, given a problem, I give you a random access computer with polynomially bounded memory, and you can reuse that memory all you want to solve the problem. For p-space, the complete problems are quantified Boolean formulas. I stick quantifiers in front. And now I ask you, can I satisfy? So no matter whether x is 0 or 1, does there exist an x2? Either 0 or 1. So that for all x3s, does there exist one? So that this evaluates the truth. Clearly, that's a much, much harder problem than, so it appears a much, much harder problem than satisfiability, where you just say, is there a solution? One string of zeros, ones which satisfy. Here you're asking, does there exist for all, does there exist, and so on. Well, just a quick picture. This is the world I live in. And this is the world many complexity theory people live in. Polynomial time computations down here, we view those as kind of the feasibly computable things. The NP problems, see non-isomorphism polynomial time problems. And then here would be those where you would have two quantifiers. See, non-deterministic polynomial time really says, does there exist an assignment? And you can easily verify. Here you could say, do there exist assignments for the first half of the variables? You know, some zeros and ones. So that no matter what you assign for the remaining half, it'll always evaluate the truth. And so on and on, this. And each of these has complete languages like satisfiability and so on. Optimization problems, control optimization problems sit in here. And it goes on top, and up there sits p-space. And please note that it's unknown to us whether p is different from np, whether p is different from p-space, and so on. And that's a startling part about complexities theory, that we have not been able to prove it. There is a very, very strong belief that this is real, that the hierarchy is infinite, and p-space is different from np, and so just as known, but we have no proof. I tell my students when they say, well, we don't know whether p is different from p-space. I tell them always, I know they're different, I just cannot prove it. Well, let me just very quickly, because we are still somewhere in the 1970s, and I would like to get to 1990, just remind you without much technical things, that the question was p is equal np is in essence the question about how much harder is it computationally to find a proof than to check the validity of a given proof. So really, it's a question about, if you wish, human ingenuity. When we solve hard problems, you know, how much luck do we need to do? What would it take to do it to do it deterministically, finding the solution without guessing and verifying? All right. And now I'll try to move on quickly to more modern stuff. And here I would like to state once more how we could view the problems in NP. We could view the problems in NP simply as those problems where somebody can give you the solution. That's what it is, but let's just look at as kind of a nice formalization. I will assume there is an all-powerful prover, and somebody's going to give a problem. For example, traveling salesman problem saying, is there a tour of length less than 10,000 miles in the traveling salesman problem? And the polynomial time verifier wants to find out whether there is or is not such a solution. And the prover can just simply send the solution. And clearly, if the prover tells exactly what cities, how to go through them in sequence, the verifier can quickly check whether that is or is not a tour which satisfies a given requirement. Or you could give here a graph, and you say, is there a graph, is there a clique in the graph of size 2000? Clique meaning subgraph where every node is connected to their other node. Finding such seems to be terribly hard. If the prover just hands you that clique, you can easily check that everything's connected to everything. So you could view the NP problems in this spirit. And people asked, here, this is the set of problems totally characterized, for which I can give you a solution which you can quickly verify. What if you're willing to give up a little bit of your total certainty? What do you believe? And so a new version was proposed, that's the version of interactive proofs. This was proposed by Goldwasser, Mikali, and Rakov, and Babai by himself in a somewhat different formulation. And here again, you have an all-powerful prover. He has all the computational power he needs, and you're not being charged for it. Some problem is stated, you both look at it, and the polynomial time verifier now starts asking questions to the prover. And to help him ask surprising, embarrassing questions, he has allowed a random source, so he can flip a coin. Right? And this prover doesn't see the flips. That's not important, but just assume that. And now what we want is the following situation, that when the problem is presented and the prover wants to know if there is a solution, the verifier, that the prover can convince him that there is, not with certainty, but with arbitrary high probability. And if the prover lies to him, that he cannot fool him, that he can be fooled with very, very low probability. And so what we say is, we say that some language, some problem set has interactive proofs, is in the IP class. If there's a protocol, how these questions can be asked, and only polynomially many can be asked. Okay? So that the verifier is convinced, if it's in, then with probability 2/3 he is convinced, and if it's not in, with probability less than a third can he be fooled. Now please note that the 2/3, 1/3 is really relevant because he can repeat the process again and again and again, and by repeating the process twice, clearly these go down. You know, you multiply those probability, multiply that probability, and they go down. And so by stretching it polynomially, these exchanges, he can force these to be as close as he wants to 1 and to 0. Right? So repeating the process, he just increases his chances. Now, if the definition isn't totally clear, let me give you an example which will clarify this very, very quickly. Let's play the following, let's look at the following set. The graph non-isomorphism problem. I give you two graphs, and I want to know whether they are not isomorphic. Namely, I'm interested in those pairs of graphs which are not identical, so that if I just relabel the edges, I cannot get them to be identical. You can think of different chemical compounds with an atom name stripped off, and you want to know whether these are the same structure or not. And now, what I want to show to you that this problem has a very interesting interactive proof. Please note, let's just start out without that. If the prover has these two, they both know what the two graphs are. If the prover quietly, randomly picks either the first graph or the second graph and sends to the prover and says, which one is it? If they're isomorphic, this guy can't tell them apart. As a matter of fact, what this prover, the verifier does, he selects one of them randomly, then constructs a random permutation so that all the edges are the edge names are scrambled, and sends it up and says, which one is it? If they're isomorphic, this guy cannot figure out which is. The best he can do is guess. Probability that he guessed correctly is 1/2. If they're different, he has all the computational power. He figures out, was it the first one, was it the second one? Because he knows which is the first one, the second one. Well, you got there something with probability 1/2. Just repeat that. If this thing has n nodes, flip a random point n times, and select, if heads, pick the first graph, if tails, picks the first graph, tails, pick the second one. You have a sequence of n graphs, permute each randomly, and send it up to the prover and say which is which. If that comes the correct sequence, that was the first, that was the second, however you pick those, you know they cannot be, they're not isomorphic. Or you know with extremely high probability they're not isomorphic. if they were the same graph, and you picked first and second and so on and scramble them, send them up, there's no way of distinguishing them. It's the same graph which was set up. So there, his ability to fool you, at best, would be 1 over 2 to the n. And the probability, if he sends you the correct sequence back, which you remember, then the probability is this high that those graphs are not isomorphic. So here's a very nice inductive proof. Any questions on this? If you understand this, you understand everything. All right? Now, what's interesting is that in the world where we live, the graph isomorphism problem is an NP. Because I give you 2 graphs and say, are they isomorphic? Well, you just tell me how to pair off the edges, and I can easily check out that they are the same graph, just scrambled edge names. Right? Therefore, the not isomorphic graph problem sits in co-NP on the other side. We have a very nice theorem. By the way, there are lots of beautiful results in here. The theorem is, if the graph isomorphism problem is NP complete, then the hierarchy is finite. That's a beautiful result. And therefore, there's strong evidence that the graph isomorphism problem is not complete finite. Therefore, satisfiability could not be reduced to it. Therefore, the fact that graph isomorphism, non-isomorphic problem, has an IP proof doesn't mean that everything here will have an IP proof, interactive proof. So, for a long time, people knew there were some interactive proofs for this class. Clearly, NP has all interactive proofs. Typically, just give the solution. And they had some here. And then an amazing thing happened. Several people got together, via email and otherwise, and Fortno, Karloff, and Lund showed that not only does co-NP have interactive proofs, but anything in the polynomial hierarchy is interactive. They got so excited, and they were so close to email that they told the world about their beautiful result. And that's a mistake. When you get a profound result, understand your techniques. Don't show it to your friends. But don't show it to your former friends. Hadi Shamir in Israel read this with great interest, and then he must have chuckled, because he said, you guys just didn't pursue it long enough. It isn't only true that everything in this hierarchy has interactive proofs. Everything in P-space has interactive proofs. And miraculously, the P-space computations are exactly those which have interactive proofs. Well, I have very little time left. Let me just mention to you how could this proof be obtained, because it's such a very unusual proof. And then I'll draw a consequence about theory proving. Well, the sad fact of life is that NP is characterized by satisfiable polyformulas. P-space is characterized by satisfiable quantified polyformulas. Polyformulas keep creeping up. And we don't understand polyformulas. We don't. We understand polynomials. You show me a polynomial and you say how many roots. I'll tell you how many roots by just looking at the degree. I'll tell you lots of other things. How many real roots? How many double roots? I can differentiate this thing. I mean, we have a beautiful theory of equations, which is very powerful and very interesting. When you show me a polyformula and say, is there a satisfying assignment, which in essence corresponds to a root, if you wish, I have no idea. I can look at it, I can stare, and we don't know anything about it. What's amazing about polynomials, well, what's amazing? What's lovely is that, for example, if you give me 2 polynomials, and I just at random pick a large integer, less than some big prime, and plug it in, and the 2 polynomials evaluate to exactly the same value at that random point, then I might as well say they are equal, they're identical. Because if they evaluate this one, then R is the root of that polynomial. If this degree is low, then it's very unlikely that I would have hit on a root because there are very few roots. Okay? And so polynomials have a very, very nice property. If I have a reasonably large range and I pick a random thing from there, and the values are the same, they're the same. We don't know anything like that about Boolean formulas. So in some sense, polynomials can be tested. Hey, who are you? Give me just your value at a random point. And if you give me that number, I got your polynomial pretty much characterized. Not totally, but with very high probability. Anything else evaluated the same, it's identical to that. Okay? And so you can really work this out. And the lovely idea which these people had is simply say, we don't understand Boolean formulas. Let's work with polynomials. And that bold idea alone solved it. And let me not torture you with all of it. Let's just say that you convert the Boolean formulas to polynomials. You pick a large prime, or becomes plus, and becomes times, negation of the variable becomes 1 minus x. And now, for all, becomes just a product, multiply together all possible values. The exist becomes a sum. Therefore, if you give me a formula of this sort, it converts to this, right? Just pluses and times. And then you have to sum here, plug in now, sum this, when you plug in 0 and 1 successively for x2, and then you multiply out, and out comes the value 2. And with little induction proof, you show that if this conversion of a quantified Boolean formula by going to the polynomial evaluates to something not 0, that quantified Boolean formula is satisfied. Wonderful. It's not necessarily 1 that the Boolean formula is giving you, but it's satisfiable if it becomes out different than 0. And so now you've got polynomials. But remember, polynomials can easily be fingerprinted by sticking a random value. And let me not go through it. What they do is simply, there's this monstrous Boolean formula, quantified monstrous Boolean formula, and we convert to polynomial, and you got to sum and multiply things, and it grows tremendously big, which you cannot do in polynomial time. But these smart guys say to the prover, please compute it, but leave x1 as x1. Run through all these sums and additions through, and you'll get a polynomial. And then I will plug in a random x, and I got that polynomial pegged. And if you gave me the wrong polynomial, next time I'll ask you, forget about x1, now give it to me in x2. And again, I'll put random one in. And at the end, I'll be down to the last variable, and that I can do myself. And if you start lying somewhere, if the prover doesn't give the right polynomial, he has to keep on lying with very high probability all the way through. And this very elegant switching to the polynomials, and then realizing that polynomials are fingerprinted by the evaluation at random points, fingerprinted with very high probability. No, it's almost like you might have slipped your fingerprint a bit, but it's really fingerprinted, uniquely almost. And out comes the proof that anything that quantified Boolean formulas, whether they evaluated true or not, can be easily verified in an interactive proof. Now, the lesson to be learned clearly there is, how do we, in other problems like trying to see how hard NP is, solving NP problems, how do we bring in the continuous mathematics? How do we rely on some powerful results in mathematics? So far, we have not found any connections. And it seems to me a little bit strange that in all the awesome arsenal of mathematics, there's nothing which seems to scratch these problems. Now, in this case, there's an example, and I would believe that one has to just very intensively search for the connections to powerful continuous mathematical theories of these combinatorial problems. And now let me draw very, very quickly some connections to theorem proof using the interactive proof ideas. When we write, let's say I have a nice formal system which proves true things only, nicely axiomatized. Now when I put a statement of theorem down and you write your proof, I will insist that the proof checker is a finite automaton which can read a block of symbols at a time, square block say, and scans the proof from left to right. And at the end it tells me there is a proof or there is not a proof. Any proof system which you have, I will very easily convert one which will be checked by finite automaton. It doesn't have to run this way. You can make it run up and down, left and right. You can make it non-deterministic, doesn't matter. Now, if I have that, then I can define what the width of the proof is. It's the longest line in the proof. I'm not interested how long the proof is. I'm not interested in adding up all the symbols. I'm just saying how wide is the proof. It's the longest line. What is the width of a theorem provable in this system? Well, the width of this theorem is the width of the narrowest proof of that theorem. So I look at all possible proofs of the theorem and pick the narrowest one. Right? So I have defined the width of a proof. If you don't like this proof intuitively, you may think that your proofs are in a straight line. Make the proof checker a finite automaton, which does just what I do, you probably do. When you check a proof, I go with fingers, does this follow from that? And I go through formulas just like you do. If you don't really do it with your fingers, you do it some other way, but fingers are necessary. And the width is nothing else but the maximal separation of the heads of the fingers while you read the proof. So the width is a very intuitive concept in proofs, intuitively satisfying. It's how far apart is information which you have to have as you run through the proof. Right? And now, a nice little amusing thing happens. We can define, for a formal system, the set of polynomially wide theorems, or those theorems of polynomially wide proofs. And it takes no time at all to show that for any formal system, the theorems with polynomially wide proofs will be always in p-space. And for every language p-space, you can define a formal system where you get those things indistinct with polynomially wide proofs. In essence, when I look at the family for all proof systems and for all polynomials, the class of polynomial wide proofs, that's exactly equal to p-space. That's not a hard thing to see at all. And now we get the nice result. The things you have interactive proofs are exactly equal to p-space. Interactive proofs are equal to p-space, which are exactly those sets of theorems which are polynomial wide proofs. So when I ask you how easily can I convince you that there is a proof, and you don't have in your lifetime enough time to read the proof, but can I convince you there is a proof by asking me questions? Can I convince you with very high probability there is a proof? And the answer is the width of the theorem determines how quickly I can convince you of that. Very strange. What do we have? If a picture is worth 1,000 words, this one is not. There just isn't enough on it. But think of a narrow proof. Okay, this can be exponentially long in the length of the theorem, but I've drawn it as polynomially wide. And that's a narrow proof. This proof could be as long as this one if I add up all the symbols, but this one is a wide proof. This theorem, that it's true, that has a proof, I can convince you in polynomial time, where this could be exponentially long. For this one, I can't. So miraculously, very strangely, the width of this theorem tells you how quickly can you be convinced that there is a proof. And you don't have time to read even a fraction of the proof. Because if this is exponentially long and I'm giving you polynomial time, it's basically off by an exponential, the length and the time I can convince you there is a proof. So very, very strange, in a very kind of beautiful turnaround. The initial impetus to develop a theory of computation came from logic, from trying to understand the Gödel, extent of Gödel type results, led Turing to do that work and so on. That led to NP type problems. Gödel asked the question, Hooke clarified it. People tried to extend and understand how could we go a little bit about NP, introduce interaction and randomization. And everybody was startled who finally saw the result that interaction, that somebody gives you answers, and randomness is immensely powerful. That you get all of piece-based computations, not with total certainty, but reasonably high probability. And you come back and it suddenly says something about that the shape of the proof tells you a lot how quickly you can be convinced whether that theorem is or is not provable without seeing the whole proof. You're seeing a minute fraction of the proof. And that's all.